Okay, well, yeah, let me start by thanking the organizers for the opportunity to speak and for putting this conference together. It's really a great pleasure to be here in person and speaking on a blackboard. Yes, I'll be talking about integral Galois model structure of Mordell Weil groups, and everything I say will be joint work with Alex Bartel, who will hopefully keep me honest. Yeah, maybe let me say, so please shout if you can't read what I'm writing, if it's not big enough. Okay, so maybe let me start with a general, kind of slightly vague, motivating problem that Alex and I were thinking about, and then I'll shortly restrict to a special case, which I'll focus on for the rest of the talk. So E over Q be an elliptic curve. And K over Q, a Galois extension with Galois group G. Then by the Mordell Weil theorem, the group of K rational points. So when you tensor this by Q to get a Q vector space, so this is finite dimensional and it comes with a G action. So it's a finitely generated QG module, or if you like, a finite dimensional rational representation of G. And sort of what data is required to determine its isomorphism class as a representation? Well, just some general fact about rational representations, that its isomorphism class is determined by the rank of E over sub-extensions of K over Q. Sub-extensions of K over Q, even can restrict to ones where K over L is cyclic. But suppose you don't tensor by Q and you want to ask sort of integrally what is this representation structure. Well, at least once you've pinned down the rational structure, there's only finitely many possibilities for what sort of the Mordell Weil group modulo torsion can look like. So integrally, if you first determine this rational representation structure, given E of K tensor Q as a QG module, this doesn't determine it doesn't fully determine the integral structure, but it does determine it up to finitely many possibilities. So finitely many possibilities for the ZG module isomorphism class. So what I'm going to be interested in this talk is, well, not the full Mordell Weil group, but the Mordell Weil group modulo torsion. So this is now just some finite rank 3 abelian group with a G action. Okay. So the general question is the following. So suppose you sort of flip this situation on its head. We want to start varying in K. So let's start now with some finite group G. And fix some rational representation of G. So as we vary, this is the question, as we vary over G extensions K over Q, where, so by G extension I mean Galois extensions with Galois group isomorphic to G, but I'm really fixing that isomorphism as part of the data. So then I can view the Mordell Weil group tensor Q sort of unambiguously as a G module. So if we vary over extensions where this is isomorphic to our fixed representation, the Mordell Weil group modulo torsion sort of integrally is just moving around between these finitely many possibilities. I think it's sort of a natural question to ask how often you see each of these possibilities occurring. Okay, so this is sort of the question, the motivating question that Alex and I were interested in. It's a little bit vaguely formulated, so I'm not telling you, for example, how to order these extensions, and the answer could depend on that. But yeah, you sort of fix the rational representation structure, and then integrally, there's just finitely many possibilities, and we'd like to understand, yeah, well, sort of how often each occurs, and if there's some sort of nice, I don't know, heuristic principle determining what these probabilities are, like whether you could distribute between these possibilities or sort of what's going on. Okay, so for the rest of the talk, I want to sort of just focus on maybe the first case where this question is non-trivial, and that's already going to be sort of interesting enough to take up the rest of the time. So from now on, so G is going to be Z mod 2Z, so we're going to be looking at quadratic extensions. So let me start by taking some elliptic curve E over Q with rank 1. And so let me start by, let me immediately impose some assumptions on E, which is just going to make sort of proving things later easier. I just want to get them out of the way now while I'm thinking about it. So I want to assume that E has full rational 2 torsion. And no cyclic 4 isogeny defined over Q. So you're sort of familiar with work on distribution of two Selma groups. In quadratic twist families, this is sort of exactly the condition that makes these nice to study. So it's sort of a clue that some Selma groups are going to be appearing shortly. Okay, and so I'm going to look at all quadratic extensions over which E gets rank 2, which from sort of what I said earlier is going to be enough to fix the rational representation structure. So more precisely, I'm going to look at this family F of square free integers. So thinking of quadratic extensions as square free integers, where E gets rank 2 over the corresponding quadratic extension, or sort of equivalent way of saying that is that the rank of the quadratic twist of E by D is equal to 1. So this is quadratic twist of E by D. Okay, so what does the Mordell Weil group over the corresponding quadratic extension look like as a representation? So for D in this family, so E K D, so that's just shorthand for Q adjoint square root of D. So when you tensor this by Q, so we've set it up so that you have one-dimensional invariance and rank 2 over KD, so two-dimensional representation in total. So this just must be direct sum of the two irreducible representations of cyclic group of order 2 as our AD over Q modules, or thinking this fixed cyclic group of order 2. So this is trivial representation. This is the Q where the generator of this group acts as multiplication by -1. Generator sigma acts as multiplication by -1. And integrally, this leaves two possibilities for what the Mordell Weil group modulo torsion can look like. So integrally, so lambda d, so that's just my shorthand for Mordell Weil group over the quadratic extension, modulo torsion. So this is now isomorphic to one of two things. So it can be sort of the same with Q replaced by Z. So direct sum of sort of invariant part and anti-invariant part. Or it could be free of rank 1 over the group ring. So it's isomorphic to sort of said G, if you like. And for example, you can sort of see these are different modulo 2, where this is 2 copies of trivial, and this is a non-trivial mod 2. Okay. Maybe going forwards, I'm going to call this one the regular representation as a way of referring to it. Okay, so the precise question then is, as you vary over all square free integers in this family, so sort of quadratic extensions where E gets rank 2, how often are you seeing each of these 2 possible lattice types for the Mordell Weil group modulo torsion? So sort of more precisely, we're interested in this limit. So the number of square free integers of absolute value up to some x in our family where Mordell Weil group modulo torsion free rank 1, so divided by the total number of size up to x. And then we want the limit of this as x goes to infinity. So does this exist? And if yes, sort of what is it? So we'll question, what is this? And yeah, this sort of expression is going to appear a few times later, and I don't want to sort of write this all out. So my shorthand for this is just going to be sort of probability within the family F, if you like, of finding the Mordell Weil group modulo torsion isomorphic to group rank. Oh, sorry. All right, so maybe the first thing that we need to do to have some sort of hope of getting a handle on this is to understand sort of what this full family of square free integers that we're looking at is. So sort of a family of square free integers where the quadratic twist has rank 1, and that's sort of very difficult to get a handle on unconjecturally, but it's at least knowing what we are supposed to expect. So this is about the denominator, if you like. So Goldfeld's conjecture. Goldfeld's conjecture tells us that we should expect. So, I mean, in quadratic twist family of a fixed elliptic curve, you expect 50% of twists to have rank 0, 50% have rank 1. So this family should contain half of all square free integers. So certainly at least grow like constant times x. Expect F to contain half of all square frees. And yeah, okay, this is certainly not known, but at least if we assume, so given our conditions on E, if we assume finiteness of Sheffer state group, then this is known thanks to work of Alex Smith. So assuming okay, let's call this star, so that the 2-part of the Sheffer state group of each twist is finite. Assume this for all D, all square free D. How do I want to do this? Okay, so if we assume finiteness of the Sheffer state group for all square free D, then this is true, by which I mean so that this family contains half of all square free integers. This is true by work of Smith. And moreover, with 0% of exceptions, a square free integer is in this family, sort of if and only if, so yeah, you have rank 1 sort of with 0% of exceptions, sort of if and only if the rank is at least odd, or sort of equivalent way of saying this, assuming finiteness of Shah, is that the two-Selma group had better be odd dimensional. Okay, and what's nice about this condition is that this is sort of really easy to understand. This is just a congruence condition on D modulo the primes of bad reduction for original elliptic curve, basically. Congruence on D modulo primes dividing or either 2 or n sub E, which is a conductor of E. Okay, but so the point is that if we assume finiteness is the Chapeau-Take group, we have pretty much complete control over this family that we're interested in. And so that's what I'm going to sort of want from now on. Maybe also let me remark that, so what's actually going to be important for us is only that this family we're working in sort of grows like some constant times x at least. And you could already have got that just by understanding the distribution of two Selma groups in this family, which has sort of been known for quite a bit longer, thanks to work of sort of Kane and Heath-Brown before this sort of new machinery of Smith came in. So yeah, in order to get control over the family we're working in, so from now on I'm going to assume this finiteness of the Chapeau-Take group and try and understand sort of what's going on given that. Now on, assume star. The alternative is to replace Mordell Weil groups with a sort of analog cooked up from two power Selma groups. So you can replace Mordell Weil group with, let me just say, 2 infinity Selma analog. If you want to avoid assuming finiteness of the Chapeau-Take group, then you can sort of rework this whole thing where you're asking about the integral representation structure of a sort of the inverse limit of two power Selma groups. So you can still sort of prove unconditional statements, but maybe they're not the ones about rational points that you really want. Okay. So, all right, with this out of the way, we have the following sort of proposition, which in some sense answers the question we're interested in, but as we'll see, it's sort of only really the start. So assuming this, we have a proportion of D where you find Mordell Weil group modulo torsion to be free of rank 1 is actually 0. So for 100% of D, you're finding it splitting as a direct sum of invariant and anti-invariant parts. And the reason for this is simply that there's a local obstruction to finding this representation term. So some local obstruction, which I'll just explain in a second, finding this. So let me just spell this out because it's going to be sort of important for what we do going forwards. So more precisely, let's fix Mordell Weil generator P for E. So just a generator for E of Q modulo torsion, which is sort of rank 1 abelian group. So fix P Mordell Weil generator for E. For E of Q. And so E has 4 two torsions, so let's just write its two torsion points as P0 up to or T1 up to T4. And then I want to look at the shifts of P by these two torsion points. So I define Pi to be P plus Ti. Right, so the reason for this, the reason why I want to consider this is any Mordell Weil generator, this is sort of a multiple of 2 away from these shifts of our fixed one by a 2 torsion point. Okay, so that's sort of why we need to do this. And then what you have is the following. Sort of criterion for telling which of these 2 lattice types you get. So you can show that at least excluding finitely many D, which, we're certainly not going to care about because we want to understand how things work on average. One has you find regular representation if and only if one of these Mordell Weil generators, one of these 4 points, is in the image of the norm map or trace map, if you like, which takes a point over the quadratic extension and just takes sum of its Galois conjugates to get a point over Q. Okay, so roughly, what is the reason for this? Well, if you forget for a second about torsion, no? Yeah, so if you forget for a second about torsion and just imagine that the genuine Mordell Weil group over the extension is either a ZG or this direct sum, then what does 1 plus sigma do on if you have sort of Z plus Z with generator actions multiplication by -1, then 1 plus sigma is trivial on this factor and is multiplication by 2 on this first one. So this is sort of saying that the norm map has index 2 inside the invariant part, so certainly no generator will be in its image, whereas in this case, 1 plus sigma just maps you precisely into the invariant part. And okay, it's a little bit fiddly when you have some torsion flying around, you need to be a bit careful, but at least excluding finitely many D, you can make this argument work. Okay, but all right, this tells us there's some natural obstruction to seeing this, because if you're a norm globally, then you better at least be a norm everywhere locally. So yeah, sort of another way of saying that is the square root integers where Mordell Weil group modulo torsion is regular representation. This is contained inside 4 families defined by purely local conditions, so Fi sort of local, where you just insist that one of these 4 Mordell Weil generators is everywhere locally in the image of this norm map. E square free, where Pi is everywhere locally a norm. And okay, we want to, F is the family of things of rank 1, so I want to at least throw in this sort of odd rank condition that I said was almost determining that, which again is just some local condition. Okay, so yeah, these families are now super explicit because they're just given by some local conditions. And how big are they? Well, you can show that sort of the most important local condition you get out of being in this image of the norm map is the following. So sort of can show if you have a prime, if you have a D in this family, then any prime divisor of D, at least where the original elliptic curve has good reduction, must split completely in the field you get by halving this Mordell Weil generator. Sort of put another way, like the important condition of being locally a norm is that you have to be a multiple of 2 at basically all of the prime factors of D, and that's what this condition is saying. Okay, but then this says that to be in this family, we're drawing basically all of our prime divisors of D out of a set of Dirichlet density equal to sort of 1 over the degree of this extension. And that's certainly a sort of a zero density family in all twists. So sort of the asymptotic for these 4 families so this grows like some constant times x over power of log, where this power is 1 minus 1 over n for n the degree of the field where the splitting, giving the splitting conditions. Which is, this field is either quadratic or biquadratic when you halve a generator. Okay, so I mean, that's the proof of this proposition, basically. There's some local obstruction to finding this representation type we're interested in, and that already forced you to be in a family that grew smaller than x, which is a full family of twists. So the sort of proportion is dropping off like 1 over some power of log.
I actually had a question, Adam. Is this? Yeah, I like this argument. Is this local obstruction sufficient, or can you, if you're ever locally normed, does this imply you're globally a norm?
No, not at all. Yeah. So as we'll see, I mean, this proportion is 0 for sort of the reason that you have a local obstruction, and then where we're going to go next is we're going to sort of look within the family where this local obstruction vanishes, and then ask this question again, basically. And so no, it's not sufficient, and we'll sort of see in a second why that is. Yeah. Thank you. Okay. Okay, and so what I'm going to say next, which maybe I'll start saying in words while I'm cleaning these boards, is that we've got a really close analogy here, which I'll try and flesh out a little bit, with what was happening in Carlo's talk yesterday with the negative Pell equation, because there again, we saw that there was this sort of, this equation was soluble for 0% square free D, because there was just some sort of fairly trivial obstruction that was stopping it happening. And however, once you sort of ask how often it was soluble again within the family where this obstruction vanished, you then sort of got a nice answer. You found a positive proportion of times that it was soluble, and there was some really nice heuristics for why you got what you got, sort of conjectured by Stevenhagen. So this is sort of exactly where we're going here. We want to ask this question again within the family where this obstruction we've just identified vanishes. So the question was whether the extension you get where you halve the Mordell Weil generator is Galois. And so the fact that our elliptic curve has full rational two-torsion sort of guarantees this, because all of the Galois conjugates of half of this point, they differ from your original thing by a two-torsion point. So yeah, this is actually guaranteed to be biquadratic when it has to be 4. Yeah, thank you. Okay, so, okay, maybe let me go for the top board that's maybe had a bit more time to dry. Yeah, so remark what I just said. So there's a close analogy here. With this negative Pell equation that featured in Carlo's talk yesterday. So this was the equation, let's call it dagger, x squared minus dy squared was minus 1, which you're trying to solve in integers x and y for fit square 3D. And yes, I mean, this is basically, so this is sort of sum, minus 1 is some norm. So this is sort of a norm problem for the multiplicative group, I guess, and we've found that we've sort of reduced to 4 kind of norm equations for an elliptic curve. And yeah, similarly, what we saw yesterday is that you know, if this is soluble in integers, then it certainly has to be soluble in sort of rational x and y, which is a purely local criterion, and it gave this upper bound of number of square 3D less than x, where this guy is soluble over z. Like just from this local obstruction was bounded by sort of x over square root of log x, where, I mean, yeah, this half is coming from sort of basically the same reason as we had over there. You basically all the prime divisors of D, they have to split completely in the field where you use square root minus 1, and that's exactly the sort of the same criterion that we have. You sort of halve the point that you're trying to test if it's a norm. And so, well, in particular, we saw that this is soluble for 0% of D. But in the family where the substruction vanished, so where minus 1 is a norm sort of everywhere locally, if you like, or a norm from rational numbers, this sort of beautiful work of Peter and Carlo says that this is soluble for a positive proportion alpha greater than 0 of D, where alpha was predicted by Stevenhagen's conjecture. Yeah. Okay, so sort of when you restrict to the family where your obstruction vanishes, you do see this being soluble a positive proportion of the time, and there's some really nice sort of heuristics for telling what this proportion should be exactly, and we now sort of know that this is true. Yeah, so this sort of motivates, sort of see where I'm going. We identified the local obstruction defining this representation type we're interested in, And so we're going to restrict the family where the local obstruction vanishes, ask that question again, and we'll hope we can prove that at least there's a positive proportion of times that we see this in that family, and conjecture exactly what's supposed to be going on. Okay. So this motivates. Fix one of these families. And amongst D, where local obstruction vanishes, how often do we actually see this integral representation structure? Okay. So, so far I've sort of told you how to rule out this representation type by one of our Mordell Weil generators not being a norm locally. Now I want to sort of answer Dan's question and say, how do you actually find it? How do you actually prove that something is a global norm? And we're going to do this via Selma groups. So I want to explain to you a sufficient condition now for finding this lattice type. So, okay, so when you define Selma groups, sort of the key thing is you have this co-boundary map from E of Q mod twice E of Q, so rational points modulo 2, and this goes into first Galois cohomology group with coefficients in the 2 torsion. And, well, the 2 torsion in quadratic twist is just canonically isomorphic to the 2 torsion in the original elliptic curve. So we could just think of this as the same group, but for the quadratic twist. And what you can show is that Mordell Weil generator being an everywhere local norm, that's equivalent to, so if you take the image of this under this boundary map, so, I mean, this is certainly in the Selma group for E, but the condition that this point is an everywhere local norm says that this should also be in the 2 Selma group of the quadratic twist. Is in Selma group of the twist. And be a global norm this is equivalent to being trivial inside the Shaffer-Hurwitz-Tate group, or if you like, is equivalent to this element being in the image of the sort of twisted co-boundary map. I mean, maybe sort of geometrically what's going on is, so we're trying to solve some norm equals given point, and this sort of set of solutions, this is a torsa for the equation like norm equals 0, and norm equals 0 is precisely sort of the defining equation of the quadratic twist. So we've got some sort of torsa under the quadratic twist, which we're forced to have everywhere local points. That puts this guy inside the 2 Selma group. And then trivial in the Shaffer-Hurwitz-Tate group is saying that this torsa generally has a global point, so that this PI is actually globally soluble. Okay. And this gives us a sufficient condition that I promise you for the following reason. Or, well, let me just state the condition. So, of the following lemma, if you like. So, if you have some D where local obstruction vanishes, so where this sort of distinguished element is inside the 2 Selma group of the twist, well, if you find that 2 Selma group to be 3-dimensional, then, well, because sort of remember that we're assuming finiteness of Sheffer-Average group everywhere, then you genuinely find this lattice type that we're after. So sort of why is this? Well, assuming finiteness of SHA. So, I mean, let's look at the Selma group. So you have 2 dimensions coming from the 2 torsion always. We have full rational 2 torsion. And if Sheffer-Average group is finite, then thanks to the Kessel's tape pairing, its 2 torsion always comes in an even dimensional chunk. So how can this guy be 3-dimensional? Well, you have to have full rational 2 torsion and you have to have 1 dimension of rank. But that's telling us that everything is in the image of this map. So in particular, our distinguished element must be in the image of this map, and then we're done. Okay, so assuming star, 3-dimensional Selma, equals 3 tells us that rank of the twist is 1. And everything is the image of a rational point. So yeah, this element must be the image of a rational point. So PI is a global norm. So you've genuinely found this lattice type. Okay. Okay, so now sort of what our test is going to be is to understand how much mileage we can get out of this, this sufficient condition. And to do that, we want to understand how often you find a 3-dimensional Selma group inside sort of family of twists that we've restricted to. Yeah, exactly. Yeah. So this sort of norm equation, yeah. So we used to trying to solve these sort of one of these 4 norm equations. Each of these equations is sort of equivalent to having a rational point on a 2 cover of a quadratic twist actually, and we're trying to find rational points on this exactly. And we sort of first imposed global points, and now we're sort of doing. Okay. Oh, cool. Yeah. So exactly that. Yeah. Thank you. yeah, okay, so the question we now want to understand, so we want to know how often we can use this, this lemma. So the question is how often is the Selma group three-dimensional for D in this family where we've sort of forced this distinguished element into the Selma group. Okay, so yeah, so maybe step back a second. So if we were working in the family of all square free choice, then this would be, so we'd sort of, this would already be known, exactly what the distribution of dimensions of Selma group is and how often you find three-dimensional Selma groups. So in family of all D, distribution of those two Selma groups is known. And this is by, well, sort of work of Kane, but building on earlier work of Heath Brown and Anna Swinnerton and Dyer. Heath Brown. But, okay, there's sort of two sort of problems. So the first problem is we're restricted to working in a family that's got density 0 in the family of all quadratic twists. So we certainly can't just sort of lift this result off the shelf. So this has density 0 in the family of all twists. But there's sort of something else that's going on, which that we've defined our family to specifically sort of force this distinguished element into the Selma group. So you sort of certainly can't expect these guys to behave randomly as they would in the family of all twists, because we've really defined our family to mess with the distribution. We've sort of forced delta pi into Selma group. Okay. So, I mean, often what you see is if you sort of restrict to some family where you've kind of by hand forced the distribution, force this extra element in, you might expect that you sort of get the same behavior, except everything is just sort of shifted by 1 to account for this. So sort of average is shifted by 1 and so on. So that's what you might expect. But it turns out that it's a little bit more subtle than this in this situation. And so to sort of state what we do, I need to describe a little bit what's going on. And this is a tiny bit fiddly to write down, so sort of bear with me. But okay, so sort of regarding the second point, sort of in fact, sort of we may have sort of accidentally, if you like, forced more elements into the Selma group. So sort of what's going on here? So, all right, where does the Selma group live? It lives in this Galois cohomology group. E has full rational two torsion, so after fixing a basis for the two torsion, you can just think of this as 2 copies of Q cross modulo squares, 2 times, so pairs of square free integers, if you like. And we have this distinguished element, and maybe it looks like some alpha I, beta I, and okay, maybe let me just write the next sentence and then comment. So, so what happens is the condition of being inside this family we're interested in. I mean, any element that sort of has coordinates kind of made up out of the alpha I and beta I, this also has quite a good chance of being inside the Selma group. So any element of sort of the space generated by alpha I and beta I, so 2 copies of this inside Q cross modulo squares, twice. This automatically satisfies Selma conditions at all places outside of some finite set. So outside of the 2 and primes of bad reduction for original elliptic curve. And so the reason is this, is that the only way this delta pi guy can be in the Selma group is if alpha and beta I are squares modulo p for sort of all primes, or essentially all primes dividing d. So if you look at some element like beta I comma alpha I, this is also locally trivial sort of almost everywhere, so it has a really good chance of being stuck inside the Selma group as well. And then, yeah, we're clearly going to have to sort of account for this in this distribution. Okay, so how we do this is just by splitting our family. So, I mean, whether or not one of these guys is in the Selma group, this is just now a congruence condition on D. So we just partition our family depending on D modulo the bad primes, and we treat them one at a time. So for each D, in sort of product of QV cross mod squares, or as V ranges over the sort of bad places for E, let's look at our family. Of D in our family, which are congruent to B modulo local squares. Okay, and then for each such B, there's some subspace, say UIB, of these problematic Selma elements such that such that for all D in this family, sort of this is the amount that's sort of stuck in the Selma group. Okay, so if you like, we've partitioned into congruence classes, and in each one of those, we have this systematic subgroup that's stuck inside the Selma group. It always contains this one point, but it might be as large as 4-dimensional. Okay, and then now I can tell you sort of what the distribution of Selma groups looks like in these families. So fix some I and B. And okay, so I mean, we've partitioned into congruence families. Some of these families might be empty because, we do need some congruence conditions on D modulo the bad primes to force this element in. And we have one technical assumption on our elliptic curve, which is that this field where we're defining splitting conditions is disjoint from the 4-torsion field in E. And this is double star. Then the proportion of twists where the Selma group quotient by this systematic subgroup is n plus 2-dimensional, so the 2 is just coming from rational 2-torsion. This is exactly as the full Selma group behaves in the family of all quadratic twists. So this is just given by these explicit proportions that I'll just write down. Okay, that's product from j equals 1 to infinity, 1 plus 2 to the minus j, all inverted. And yeah, so this is for any, so I'm insisting the sum group is odd dimensional, so this is for any n satisfying that parity condition. Okay, so the sort of slogan is that we've found the distribution, two sum groups in this fin family. Once you quotient by the systematic subgroup, it just behaves exactly as you would expect it to in the family of all twists. So, sort of corollary of this is for B, where the systematic subgroup is as small as possible, so it just contains the point that we really wanted to force in, then we find that the two-sum group is three-dimensional. About 41% of the time. So in particular, we finally find this lattice type that we're interested in for at least 41% of twists in this family. Maybe let me just, assuming this condition about the interaction of halving the point with the four torsion field on E. Okay. And yeah, so it genuinely happens quite often that when you split into these congruence families, you find the systematic subgroup is as small as it can be, sort of for every single B, so then you're really picking up this regular representation sort of 41% of the time. Okay. So in the last sort of couple of minutes, I want to say, what do we actually expect the answer to be? So maybe while I'm cleaning this board, let me say that, so we prove really quite generally that if you're working in some family of quadratic twists where you're defining, where you're sort of imposing splitting conditions on each of the primes, then we're able to understand the distribution of two sum groups in this family, at least with this assumption on how your splitting conditions interact with the four torsion. And we sort of find exactly the same as some systematic subgroup. And once you kill that, you get the distribution that you maybe would have sort of naively expected from knowing how it behaves over all twists. Okay. So finally, what is the actual answer? So for the twists that we're interested in, inside the Selma group modulo two torsion, there's two non-zero elements. So one is this element we forced in that controls whether PI is a norm, and one is the Mordell Weil generator of the twist, which would sort of rank 1 by assumption. And the heuristic is that this Mordell Weil generator, sort of without knowing anything more about it, we expect it to sort of equidistribute in some sense, amongst these non-zero Selma elements. So heuristic is that delta sort of D of this Mordell Weil generator equidistributes over non-zero Selma elements. So this leads to conjecture that probability within this family of finding the regular representation so you just condition on the size of the Selma group and then impose this heuristic. So sum from 0 up to infinity, the proportion where the Selma group is R-dimensional divide by 2 to the R minus 1, which is the probability that sort of this random element coincides with this. You believe this heuristic, and you just compute the answer. And what you find is if the systematic subgroup is as small as it can be, you actually genuinely get equidistribution between these two lattice types. But as the dimension of the systematic subgroup grows, it gets harder and harder for these two elements to coincide, and it gets harder to find this regular representation as the lattice type. And the numbers drop off, 1 over 8, 5 over 64, and 29 over 1024. And yeah, maybe let me leave that there.
Thank you, Adam, for the nice talk. Are there any questions at all?
No, yeah, absolutely. Yeah.
Alexei was saying that.
Yeah, go on, yeah.
Yes, one can interpret this in terms of finite proportion of those which are ever locally soluble by the global ones.
Equations for this principle of homogeneous spaces. You write them down, or?
Yeah, I guess so. I mean, yes, I mean, we know what the sort of principal homogeneous space we're looking for is. It's just the image of this Mordell Weil generator under the boundary map. And yes, I suppose that from, yeah, I mean, if given a particular elliptic curve, write down what does this generate? What is this generator? Push it through the boundary map explicitly, and then yeah, from there you can write down the sort of corresponding two cover. So I'm
Should
fairly
it be possible
sure,
to write them down as sort of using Quadratic polynomials, and like y squared equals some Quadratic? I mean, because every two torsion element with points over locally is written like this, and then you should, I don't know. I mean, so this is a well-trodden kind of area. I mean, there's all these papers by people who looked at the families of quadratic twists, of principal spaces, and just and using exactly this idea of Swinton-Dyer, like when you want to show that it's not possible for two torsion subgroup of the H-squared group to have rank 3, because of Castle's, when in the presence of two torsion points. So it's worth, I don't know, looking at these papers.
Yeah, no, absolutely. Yeah, thank you. Yeah, and maybe one sort of comment is that, yeah, I mean, how might you go and prove this conjecture? So by analogy with this sort of negative Pell equation, if you want to move beyond the two Selma group, you have this distinguished sort of homogeneous space, and you want to test whether this lifts first to the 4 Selma, which you can do with the Castle's tape pairing, and then sort of successively test if it lifts to the 8 Selma and so on. And yeah, I think there's sort of quite good hope that using this method that Smith introduced and that Carlo introduced in his talk, that you'd be able to potentially pull that off. Yes, I think. I mean, so it quite often happens that just for all B you get dimension 1, and then you find equidistribution. And when I was sort of preparing this talk, I was looking up an example where you get a larger systematic subgroup, and I had to search quite a long time before I found an elliptic curve where this happens. But I think, these congruence conditions that distinguish between each of the possibilities are a little bit complicated. And so I think in general, you just get some sort of weighted sum of these where it probably really depends on like what your elliptic curve looks like modulo bad primes. And it's probably a little bit kind of an ad hoc recipe each elliptic curve, I'd imagine. Yeah, thank you.